So today I'm going to talk about the small signal operation of MOSFET. Okay, and basically we'll actually head towards amplification. Okay, so consider a circuit, a basic simple circuit to begin with, that is something like this. Let me. Okay, so a basic circuit is something like this. That is, sorry, my mistake. Let me draw the circuit. Okay, so then there is a resistance and this is MOSFET, and this is a simple circuit already. So a current is flowing in this direction. This is my ID, and I have actually coupled an AC along with the DC at the gate. So remember, the DC at the gate is actually for biasing reason, and the AC at the gate is actually my small AC signal. Now if I apply a KVL at this point, okay, at this point I'll get this equation: ID is equals to VDD by RD minus 1 by RD into VDS. Now if I draw this straight line, then I will get this curve, this line basically. And if I actually superimpose the various ID/VD curves, then I will get this picture, the whole thing. So this is straight line, black line, that is this one, is known as load line. I have already discussed these things in the class, but to give you guys an idea. So now, so what I'm having right now, so I have different gate voltages. You can see that different gate voltages and different, I have a set of drain to source voltage. Right now I'm giving the input, AC input at the gate. I'll be measuring the output at drain to source. So my input is gate, consider my input is gate, and my output is drain. So now if I use this particular curve and draw the input versus output voltage curve, that is known as voltage transfer characteristic curve, then it will be something like this. You can easily see this one. So my x-axis becomes VGS and my y-axis becomes my output, that is VDS. And see that the circuit I have actually drawn in the previous slide. So moving back towards the previous slide again. Now see that I actually derive this VTC curve from this curve. By how you may say this, because just see this one, you can easily understand this. So say this particular output, that is zero current, right? This is a zero current, is occurring when the gate voltage is below threshold voltage, right? And what is the operating point? You just see this one, the load line is actually intersected with this zero current that is at A, and the value is VDD, right? The value is VDD, and you get this one. See this? You get this one. So before threshold voltage, your MOSFET is turned off, your current is zero, but your drain to source voltage is VDD. Okay, and what is happening here? And see that when you are decreasing when you are increasing the gate voltage, right, you're increasing the gate voltage at this direction, your Q point is actually shifting towards this direction, right? So initially it was at lower gate voltage you got output VDD, and then as you increased the gate voltage, you will be in this operating point, then this operating point, then this operating point right here, then this, and then this, right? Okay, fine. So see that till B, your operation region was at saturation, right? And after B, it is in the linear or triad region, right? Now you can easily see that after B, so this region actually holds a very small drain to source voltage, right? So you can easily point out the B and C points. It was very small, right? So see that here also B and C actually meaning a very small value in drain to source or output voltage. So you can easily understand I have actually drawn this curve from the previous curve. Now, meaning that this region should be linear. This region was cut off, and this region is saturation, right? So now let's arbitrarily take a point, an operating point, that is this Q right here. And if I put an input signal, a small AC signal like this at gate, this is small AC signal. So this is again this signal. If I apply this one, see that this is the VGS exists, the input, right? Get to source. Now let's forget about the DC supply, because the DC supply is here to give you a bias voltage, and I want it to be in the saturation region. Okay, so now if I apply a small VGS at the gate, so it actually, see that you can easily understand this one, this negative point here is actually this point, right? You can see this, right? This, now this positive point becomes this point, right? And this negative again becomes this, right? So you can easily understand this curve will translate to this output, which is quite large than the input. So I can easily say that the input will be actually amplified at the output, considering VDS to be my output. So this was my output. Now, why I have chosen the saturation region for amplification? Why not triad region? Why not? Why not use this BC region? Right? Say consider a Q point right here. Consider. And if I have actually applied a small AC signal, see that the same thing. Now this point would have been translated to this point, and this point would have been translated to like this point, right? And if I have drawn the curve according to it, you can easily understand it would have been something like a very small something, right? Very small. So rather than amplifying, the output signal would have been attenuated, which is what I don't want. So this is not desired. That's the reason I'm not choosing the triad region. I'm choosing the saturation region because it has a higher slope. Basically, the higher the slope, the more gain you get. Okay, the more gain you get, the higher the slope. Just remember this. So again, why actually giving a DC bias? Why not just give an AC, small AC signal at the gate? Why not do that? Let's consider this for a moment. If I actually don't apply this DC bias, then what would have happened? See that it's very simple to understand from the previous curve, okay, which is actually quite okay, I'm giving an idea what will happen. So this is my characteristic curve. Now see that if I don't apply any get to source voltage, DC voltage, actually get to source DC voltage or bias voltage, then it will be initially at turn off, right? Then if I apply directly an AC, small AC signal, it is a high probability that AC signal in at the positive portions it will turn on. Basically, in the most probably it will be on the triad region or something, gets attenuated. And what about in the negative region? I'm considering about the NMOS. Okay, I'm considering about NMOS. So at the negative gate voltage, the NMOS is turned off, and I know turned off means what voltage? output is VDD, constant VDD. See that you won't be getting this. Maybe you'll get an attenuation version of this, right? An attenuation version of this, but what would be the output? Something like this, huge, right? So instead of getting an amplification, you're getting some attenuation at some portions and turn off at other portions. Basically, the input signal is totally distorted. So that's the reason I need to have bias voltage. That's why I don't give an AC signal directly input to an NMOS or PMOS for amplification. So I actually use the DC voltage source at the gate to bias it on the saturation region for gain, and then I choose a Q point, suitable Q point. We will try to take the Q point in between B and A. Okay, so to get a good swing at both sides. So that's the reason we choose actually the saturation region for amplification. Now let's move forward. Now see that there is a case here saying that there are two Q points, Q2 and Q1. So what will happen? So see that it's very simple. Q1, if you take another thing I would like to mention, see that your input signal was something like this, and it is translated at a gain, right? It is gain, it is, you're having a gain, but the gain is something like this. Okay, the signal is similar but exactly opposite, so you have a phase shift. You have to remember this. Okay, so now let's move forward. No, so say this is your Q point, Q1. What will happen now if you give an input signal of something like this again? What will happen? Let's try to understand. So as your positive voltage will increase, you'll move towards this region, right? So it will mean that this, due to the phase shift, it will be the negative portion of your output signal. And as you can see, this is your boundary line. After VDD is shut off, turned off, so your output signal won't have proper leg room. That is, we call it leg room. So as you can see, your signal, and if you choose proper your signal, actually sorry, if you choose Q1, right, if you choose due to the right, if you choose Q1, okay, let me just erase these things for you first. Okay. Now let's begin again. Now if you choose Q1, so this is your boundary line, and you give an input something like this. Due to phase shift, your positive will be, your Q1 will be moving towards this portion, and for negative, your Q1 will be moving towards this portion. So definitely for negative portions, you'll be moving into a turned off or cut off region. That means lack of leg room, and the opposite thing will be happening. So you can easily understand, for positive portions you will be moving towards this region, and so definitely you will be lacking the leg room. You'll be moving towards triad region, you'll be lacking the headroom. Okay, so these are the problems for these two extreme points, Q1 and Q2. So Q1 will suffer from leg room and Q2 will suffer from headroom. Okay, now so there is one small signal equivalent circuit for models which will help us to actually easily calculate the gain of the amplification. So it is known as the pi model. You can see that it is known as the pi model. So basically what you can do is, there are two different circuits you can see, right? So if you take the output resistance, if you consider the output resistance, then this is your model, and if you don't consider the output resistance, then this is your model. So what does this mean is, you can actually replace a simple you can actually replace a MOSFET using this model. So say for example, this is your drain, this is your gate, and this is your source. Instead of drawing this whole thing, instead of drawing this thing, you can actually draw this circuit, which is actually familiar to us in terms of analyzing it, right? So there is some current source, resistance, so it can be done. Okay, so that's that. So this is a dependent current source. The value actually depends on GM/VGS. GM is a transconductance parameter. We'll get to know it in a few moments. Okay, so VGS is your gate to source AC signal. So small VGS means the quantity is AC. When you find large VGS, the quantity is DC. So this is, I mean this to be DC, this is your AC. Okay, fine. So now when you consider the output resistance or saturation region resistance, you need to put a parallel resistance to the GM/VGS current source. Okay, so now let's move forward. So when you choose the finite output resistance, if you consider the finite output resistance R0, actually that, what is the practical thing that happens is, there is a reduction in the voltage gain. Okay, because initially if you don't consider that, it means your R0 is infinite. R0 is infinite, which actually in turns increases your gain. And if your R0 is not equals to infinite, which in turns decreases your gain. Basically that's the thing. So here is a term I have written. See that V small v big letter GS means you have both DC parameter and AC parameter. So now, so we're talking about precisely this scenario right here. So see that AC plus DC, small v big G big S. So you have AC plus DC. So AC plus DC means this thing right here, right? AC plus DC means this thing right here. Just remember this. So now if you put the equation to the, as I'm choosing the saturation region, so I will use the saturation region equation, and if I put the replace the value of VGS like this one right here, then it can be written in this form, which actually represents, see that this term right here, see that this term right here is nothing but a proper DC current. Okay, and see that this is entirely an AC component. Okay, so this is an DC component, this is a entirely AC component. This is a mixture, some sort of mixture, AC plus DC, right? There is some AC here, there is DC here, right? So AC plus DC mixture. So now, so we always want linear amplification. So what does actually linear amplification means? You give a signal something like this, it should look something either like this in terms of amplification, or like this, a phase shift but looks similar, right? So this is linear amplification. So what is nonlinear amplification then? Let's try to understand what is nonlinear amplification, and why don't we actually want nonlinear amplification. So if you give an input, nonlinear amplification may result in something like this. So see that maybe your positive portions doesn't amplified in a greater sense, or amplified by a huge number quantity, but your negative portions has been, so it is not actually similar on both the half cycles, right? So this is known as nonlinear, and we don't want this. Okay, we don't want nonlinear amplification. So to avoid nonlinear amplification, we need to avoid nonlinearity. So how can nonlinearity be avoided? So you can easily see this equation right here, VGS square, which means a parabola which is not a linear term, so nonlinear. So how can we avoid this term? So see that VGS square, if I give this is a AC component, right, VGS. So if I give that VGS to be very small, like on the order of some millivolts, so it might mean, like, say for example, to give you guys a good idea, so say for example 0.01, okay, 0.01. so it basically means 10 milliamps, most probably it's 10 milliamps, right? So 0.1 means 100 milliamp, 0.01 means 10 milliamps. So 10 milliamps, and you get to square it, so it becomes very, very small. Okay, so which is actually negligible then. So basically you can avoid this whole term, the AC component, by actually choosing your AC signal, the input AC signal, that was this right here, this one or this one, to be very small. So if you choose the AC signal to be very small, what you get is you can actually avoid this term. So your nonlinearity is removed. Then what you have, this DC component entirely, okay, and this component comprised of DC and AC. So we actually will look for this one as the amplification. Okay, now to move on further, so let's consider now this is my AC component right now, because this has the AC term in it. Okay, so if I take it as the AC component, so now, so if I now break down the ID, so small ID would be that term, okay, the AC term, that means VGS minus VT into VGS, right? This is the small ID, and the big ID is the first term. Okay, so now let's move on to this one. So see that this is the thing I have tried to show you. So see that ID is equal to Kn VGS minus VT into VGS. Now if I just take the IG, I divide the whole equation by VGS, then I find ID by VGS is equal to this one, which is actually known as GM. So what is GM? GM is actually transconductance. So see that why a name such is given to GM, because resistance is actually voltage over current, right? And it is current over voltage, that means conductance. So it has some conductance portion to it, and as the VGS is input and ID is input, so it is the transfer characteristics. So transconductance, so GM is transconductance, and the equation is Kn into VGS minus VT. The interesting thing to remember right here is, see that GM can be determined by, or found by DC analysis of DC will give you the analysis of DC will give you the result of GM, so not AC, because there is this DC portion here, right? And process parameter Kn, you need to know that. So there are some biasing schemes. Let's talk about some biasing schemes. Like, first of all, biasing by fixing VGS. So what does this mean? Say for example you have okay, by biasing, what does I mean is something like this. So you recall that I have put AC plus DC. So this DC is my biasing. I'm biasing the whole NMOS operation to saturation region. That was my goal. So this certain biasing can have different techniques. So I'm now talking about biasing techniques. Okay, So the most easiest one is just simply give a DC. So just biasing by fixing VGS. This scheme is known as biasing by fixing VGS. So you can easily see that the gate and source voltage is fixed, but it has some very crucial problems with it, because if let me show you guys. So biasing by fixing, so this is the circuit, you can see that. So gate to source voltage is fixed as okay. So now what happens, consider extreme case, that is when you have two different MOSFETs of a same batch. If the extreme case arise, then both the MOSFET will not have the same threshold voltage. One will have a higher threshold voltage, one might have a low threshold voltage. In that case, your gate to source voltage is fixed. What happens? One turns on at very early stage, another turns on at a later stage. What happens is you're fixing VGS. So two different MOSFET means two different values of current. It's a problem. You can easily understand. It's a problem. So consider you are using this MOSFET right here. Now now your circuit is burned due to any reason, I don't know, whatever the reason. Say now you want to replace it, so you will replace with a same batch MOSFET, right? So now you have taken another MOSFET, like say device 2 from the same batch. Now you want to replace it. When you will replace, if that's the case, the extreme MOSFET, that is, now it will turn on at an early stage, but you will get a different current, meaning a different Q point. So your Q point shifts drastically. So it may not be in this sweet spot right here. It may be shifted towards this point or this point, you never know. So that's a very bad scheme, fixing VGS. Okay, fixing VGS, that's not a good scheme. So let's talk about biasing by fixing VG and connecting a resistance in the source. So how that looks, let's see. So just you're fixing, same thing happen, but you have actually put a resistance, series resistance at the source, right? So this actually improves the quality a bit better, because you'll understand why. Now see that your gate voltage is fixed, right? Now gate to source voltage, say for example, I'm giving an idea, due to any reason, due to variation of temperature, because as you know, when the current will flow through a MOSFET, it will heat up, so that heat will cause the current to increase or decrease, whatever it is. Say due to any chance your ID increases. If your ID increases, what happens? Let's try to understand. If your ID increases, your VG is fixed. Okay, your VG is fixed. Initially your VG was fixed, VGS is fixed. So ID increases, that will turn your VS. Now ID increases means your VS will increase, source voltage will increase, because there is a resistance right here. Now if your VS increased, then VGS will decrease. So that means this RS resistance will have a negative effect. So if VGS is decreased, your situation will look something like this. See that? So see that this one was, say for example, an initial point. If ID is increased by any chance, then the Q point might shift towards this point, but the variation is very small. Q point shifts very little. Or if you use a different batch of MOSFET to replace, then again that starts at an earlier point, then the Q point shifts a bit only, not by a huge point, right? So if you use connect a series resistance, then it is good, actually not bad. So it gives some sort of immunity from the temperature. Okay, so let's try to see the other possible biasing schemes, that is drain to gate feedback resistance. So this scheme looks something like this. So just what you're doing, you're actually putting a resistance between drain and gate, nothing else. So the drain and gate, you know that the gate current is 0, so the gate current is 0, so the drain voltage and gate voltage is same, that means it is in saturation region. And okay, so but this gives a very good thing, that is, as VDS and VGS is same, what happens is interesting thing happens. If by any chance ID increases, okay, if by any chance ID increases, your VD drain to your drain to source voltage, right, your drain to source voltage will also increase, right, your drain to source voltage will also increase. And if your drain to source voltage is increased, then what happens is, let me show you, I have this, so this is the circuit, right? So see that VDS is equal to VGS, which is VDD minus VD. So what happens is, see that your drain voltage increases, and drain voltage is nothing but ID into RD, right? So sorry, my mistake, the drain voltage decreases because your ID increased, right? ID increased, so significant drop will be appearing at RD, meaning that your drain voltage will decrease. That means your gate voltage will also decrease. As your gate voltage decrease, then it will have a negative feedback that your drain current will actually decrease. So interesting thing. So that's good. Okay, so now let's talk about the best solution, that is classical discrete circuit bias arrangement, that is also known as voltage divider biasing. It is very much stable, and it is actually practically used in various circuits. So this is the arrangement. Not going to talk about all the benefits, because I have already broken down everything. This source resistance gives you good immunity against temperature, and this drain resistance actually gives you a negative this source resistance and drain resistance gives you good negative feedback, so keeping your ID drain current stable at all times. So this is a very good voltage divider arrangement, which is actually practically used. This is the practical implementation version. So that includes actually two different power supplies. Okay, so we'll be talking about solution of maths in the next lecture. Thank you guys for watching. I would suggest you guys read the slide, go through the textbook, Cedric Smith textbook, microelectronics, and practice these things at home and make things clear. Thank you guys.